In electrical systems, proper grounding and bonding are critical for safety and functionality, especially in subpanels. The situation you described involves a subpanel fed from another subpanel using service entrance cable, or SE cable. Let's break down why the initial configuration didn't work and why your boss's solution did. When you bonded the neutral and ground bars in your panel by screwing in the bonding screw, you essentially created a parallel path for neutral current. This parallel path included the equipment grounding conductors. According to electrical codes like the National Electrical Code, or NEC, the neutral conductor should only be bonded to ground at the service entrance, or the main panel. By bonding the neutral and ground in the subpanel, you created what amounts to a ground fault loop. This is because the current from the neutral conductor was now able to flow back to the source through both the intended neutral path and the equipment grounding path. This division of current can cause several problems. Firstly, it can lead to nuisance tripping of circuit breakers, as the ground fault current could be detected by ground fault circuit interrupters or arc fault circuit interrupters. Secondly, it can cause electromagnetic interference, or EMI, as the current flowing through the grounding conductors can radiate electromagnetic fields. Thirdly, it can create a shock hazard, as the equipment grounding conductors could become energized if there is a fault in the neutral conductor. The bare green wire in service entrance cable is intended to be the equipment grounding conductor. In a properly wired subpanel, the neutral conductor should be isolated from the panel enclosure and connected only to the neutral bar. The equipment grounding conductor should be connected to the ground bar, which is bonded to the panel enclosure. Your attempt to bond the neutral bar to the panel enclosure by installing a bonding screw was incorrect in this scenario. The reason it didn't work is because it perpetuated improper grounding configuration. The core issue was that the neutral conductor in the SE cable was cut at the upstream panel, meaning the subpanel was not receiving a proper neutral connection from the source. When your boss had you cut the neutral conductor in your subpanel and connect the bare green wire to the neutral bar, the system began to function. Here's why. By connecting the bare green wire to the neutral bar and disconnecting the original neutral conductor, you effectively made the bare green wire serve as the neutral conductor for the subpanel. This worked because the upstream panel had a cut neutral, and the bare green wire, intended as the ground, was now carrying the neutral current back to the source. While this made the circuits work, it created a dangerous and code-violating situation. The equipment grounding conductor is not designed to carry neutral current continuously. It is intended to provide a low impedance path for fault current to flow back to the source in the event of a ground fault, thereby tripping the circuit breaker or fuse and clearing the fault. By using it as a neutral conductor, you've compromised the safety of the system. Let's clarify the correct way to wire our subpanel. Firstly, the neutral conductor from the source panel should be connected to the neutral bar in the subpanel. This neutral bar should be isolated from the subpanel enclosure. Secondly, the equipment grounding conductor from the source panel should be connected to the ground bar in the subpanel. This ground bar should be bonded to the subpanel enclosure. Thirdly, there should be no direct connection between the neutral bar and the ground bar in the subpanel. The only point where the neutral and ground should be bonded together is at the service entrance. Fourthly, the size of the conductors used for both the neutral and equipment grounding should be appropriate for the load they are expected to carry, according to the NEC tables. In the NEC, specific tables like 310.15, formerly 310.16, detail ampacities of conductors based on their size and insulation type. Also, 250.122 dictates the minimum size of equipment grounding conductors. The correct solution to your problem involves properly terminating the neutral conductor at the upstream panel. Find the cut neutral wire and connect it to the appropriate neutral terminal in the upstream panel. Once this is done, revert the wiring in your subpanel to the correct configuration. Disconnect the bare green wire from the neutral bar. Connect the original neutral conductor from the source panel to the neutral bar in your subpanel. Ensure the neutral bar is isolated from the panel enclosure. Connect the bare green wire to the ground bar in your subpanel. Ensure the ground bar is bonded to the panel enclosure. Remove the bonding screw that connects the neutral bar to the panel enclosure. This ensures that the neutral and ground are only bonded at the service entrance. After making these corrections, test the system to ensure that everything is working properly and that there are no ground faults. Use a multimeter to check for voltage between the neutral and ground conductors at various points in the system. There should be little to no voltage present. If you find a significant voltage difference, it indicates a problem with the grounding or neutral connections. It's also important to understand the role of the main bonding jumper. The main bonding jumper is a conductor that connects the grounded conductor, or neutral, to the equipment grounding system at the service entrance. Its purpose is to provide a low impedance path for fault current to flow back to the source, ensuring that the circuit breaker or fuse will trip quickly and clear the fault. In a typical residential service, the main bonding jumper is often a bonding screw or strap that connects the neutral bar to the metal enclosure of the service panel. In larger services, it may be a separate conductor that is sized according to the NEC table 250.28. When dealing with subpanels, it's crucial to remember that the main bonding jumper should only be present at the service entrance, not in the subpanels. Adding a bonding jumper in a subpanel creates the parallel neutral path and the potential for ground fault loops as described earlier. Always consult the latest edition of the National Electrical Code, or NEC, and local electrical codes for specific requirements related to grounding and bonding. Electrical codes are updated regularly to reflect changes in technology and best practices, so it's important to stay informed. Furthermore, consider the specific characteristics of your electrical system. The size of the service, the type of loads being served, and the presence of sensitive electronic equipment can all influence the design and implementation of the grounding and bonding system. For instance, if you have sensitive electronic equipment, you may want to consider using a separately derived system, such as an isolation transformer, to provide a clean ground reference for the equipment. In summary, when dealing with subpanels, remember these key principles. Firstly, isolate the neutral bar from the panel enclosure. Secondly, connect the equipment grounding conductor to the ground bar, which is bonded to the panel enclosure. Thirdly, ensure that the neutral and ground are only bonded together at the service entrance. Fourthly, follow all applicable electrical codes and regulations. Fifthly, if you are unsure about any aspect of the electrical work, consult a qualified electrician. Electrical work can be dangerous, and it's always best to err on the side of caution. By following these guidelines, you can ensure that your subpanel is properly grounded and bonded, providing a safe and reliable electrical system. Remember, safety is the top priority when working with electricity. If you're not comfortable performing electrical work, always hire a licensed electrician. Improper wiring can lead to electrical shocks, fires, and other hazards. The original issue of no continuity suggests that the intended grounding path was incomplete. Continuity refers to a complete path for current to flow. In a properly grounded system, there should be a low resistance path from any point in the equipment grounding system back to the source. This path allows fault current to flow quickly, tripping the circuit breaker and clearing the fault. When you initially checked for continuity and found none, it indicated that there was a break in the grounding path. This could have been due to a loose connection, a corroded conductor, or a missing bonding jumper. By correcting the wiring and ensuring that all connections were tight and secure, you restored the continuity of the grounding path. However, it is important to verify the integrity of the grounding system with appropriate testing equipment, such as a ground impedance tester. This tester can measure the impedance of the grounding path and ensure that it is low enough to provide effective fault clearing. In addition to the points already covered, let's also discuss the impact of voltage drop. Voltage drop occurs when the voltage at the load is lower than the voltage at the source. This can be caused by long wire runs, undersized conductors, or high current draw. Excessive voltage drop can cause equipment to malfunction, overheat, or fail prematurely. To minimize voltage drop, it's important to use conductors of the appropriate size and to keep wire runs as short as possible. The NEC provides guidelines for calculating voltage drop and for selecting conductor sizes that will minimize voltage drop. Also, consider the impact of harmonics. Harmonics are distortions of the sinusoidal waveform of alternating current. They can be caused by nonlinear loads, such as electronic ballasts, variable frequency drives, and computers. Harmonics can cause a variety of problems, including overheating of transformers and conductors, nuisance tripping of circuit breakers, and interference with electronic equipment. To mitigate the effects of harmonics, it may be necessary to use harmonic filters or to oversize transformers and conductors. Furthermore, it's critical to understand the importance of proper overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. These devices should be selected and installed in accordance with the NEC and the manufacturer's instructions. It's important to ensure that the overcurrent protection device is properly sized for the circuit it is protecting. An undersized device may trip unnecessarily, while an oversized device may not provide adequate protection. When working with electrical systems, always use appropriate personal protective equipment, or PPE. This includes safety glasses, insulated gloves, and arc-rated clothing. Before beginning any electrical work, de-energize the circuit and verify that it is de-energized with the voltage tester. Follow lockout-tag-out procedures to prevent the circuit from being accidentally re-energized while you are working on it. In your specific situation, the initial lack of a neutral connection at the subpanel created an imbalance in the circuit. When the neutral is missing, the voltage on the two legs of a 240-volt circuit can become unbalanced, leading to some appliances receiving too much voltage and others receiving too little. This can damage sensitive electronic equipment and create a fire hazard. Furthermore, the practice of using the equipment grounding conductor as a neutral is extremely dangerous and can have serious consequences. It violates the basic principles of electrical safety and can put people's lives at risk. Remember, the equipment grounding conductor is intended to provide a path for fault current to flow back to the source in the event of a ground fault. It is not designed to carry neutral current continuously. Using it as a neutral can overload the conductor and cause it to overheat, creating a fire hazard. It can also create a shock hazard, as the equipment grounding conductor could become energized if there is a fault in the neutral conductor. To reiterate, the proper sequence of events for resolving this issue would have been: firstly, identify the cut neutral conductor in the upstream panel. Secondly, reconnect the neutral conductor to the appropriate terminal in the upstream panel. Thirdly, disconnect the bare green wire from the neutral bar in your subpanel. Fourthly, connect the original neutral conductor from the source panel to the neutral bar in your subpanel. Fifthly, connect the bare green wire to the ground bar in your subpanel. Sixthly, remove the bonding screw that connects the neutral bar to the panel enclosure. Seventhly, test the system to ensure that everything is working properly and that there are no ground faults. By following these steps, you can ensure that your subpanel is properly grounded and bonded, providing a safe and reliable electrical system. Always remember to prioritize safety when working with electricity. Take the time to understand the principles of grounding and bonding and follow all applicable electrical codes and regulations. If you are unsure about any aspect of the electrical work, consult a qualified electrician. In conclusion, understanding the principles of grounding and bonding in electrical systems is crucial for ensuring safety and reliability. The scenario you described highlights the importance of proper neutral and ground connections, the role of the main bonding jumper, and the potential hazards of improper wiring. By following the guidelines outlined in this discussion and consulting with qualified professionals, you can ensure that your electrical system is properly installed and maintained.